Okay, thank you. So this is the last contributed talk of this session, and it will be given by H Yokota on three-dimensional observations of polar domain boundaries in ferroelastic materials. Thank you.
Thank you very much for the introduction. And today I'm going to talk about the polar nature of the domain boundary in ferroelastic materials. And we have a lot of talk about domain boundary in the morning. And they are always talking about the head-head and tail-to-tail domain boundary. But now I'm going to talk about the different thing about the domain boundary. So the major thing that I'm investigating now is ferroelastic material. So it's nothing to do with ferroelectric domain boundaries. So this is the outline of my talk today. I'm going to show you two examples of the ferroelastic material for our experiment. So now let me begin my presentation from the introduction. And as you know, the domain boundary becomes one of the hot topics in these days. And here I plot this number of the publication as a function of year. And as you can see that the number of publications related to domain boundary increases monotonically, and also it reaches almost about 30,000 according to the Web of Science now. So for a long time, domain boundary have been considered as a wall which separates the different domains, but now the situation is changing. So before, everybody is trying to grow a single crystal or untwinned crystal, but now the situation is completely changes. We are trying to use domain boundary. So because thanks to the development of the experimental technique, we are now able to measure the physical property as a domain boundary, and it completely changed our concept about the domain boundary now. So there are a lot of projects trying to use domain boundary for the application, and we call this tendency as domain boundary engineering. And because the density of domain boundary can be extremely high compared with domain itself, there is a possibility to use domain boundary for the high density memory devices and also microwave device and transducer and so on. So here I summarize some of the exotic property observed at domain boundary in these days. And for example, electromagnetic coupling and photovoltaic effect and superconductivity have been reported at domain boundary in various oxides. And among them, I'm now interested in the ferroelectric property observed at domain boundary in ferroelastic materials. So the polar nature of the domain boundary in ferroelastic material have been predicted in 2008 theoretically, and this group also tried to measure the polar nature of the domain boundary by using an aberration-corrected TEM, and they reported a result in 2012. So what they really observed is the displacement of the titanium atom as a domain boundary. And according to the displacement magnitude of the titanium atom, they estimate this magnitude of the spontaneous polarization, and it is almost the same value with the normal ferroelectric materials. So this result is very attractive. However, there are some problems that we need to consider about this experiment. For example, in the case of TEM, they only observe one type of domain boundary, although there are several different domain boundaries in ferroelastic materials. And another thing is during the sample preparation, because this is a TEM measurement, so they need to prepare a very thin sample by milling or polishing. So during this kind of procedure, ferroelastic material can be completely change its property or domain boundary structure. So I think it is necessary to investigate the crystal without any special treatment to conclude the polar nature of the domain boundary in the case of ferroelastic materials. So this is our motivation to investigate the ferroelastic material by using our method. So now I'm going to talk about the experimental technique and the results. So we use second harmonic generation as a probe for achieving our aim. And the second harmonic generation is a nonlinear optic effect. And when the incident beam enters into the crystal, it generates a second harmonic generation whose wavelength is half of the fundamental wave. So there are several advantages to use second harmony generation for our purposes. And firstly, SHG is very sensitive to the change of the spontaneous polarization. And also, using our scanning system, we can obtain the three-dimensional images of the domain structure without any distraction. And thirdly, because SHG is related to the third-rank detensor component, we can determine the symmetry of the domain boundary. So it is very important and necessary to determine the symmetry because piezoelectricity is not enough to confirm the polar nature. So this is the optical system that we are using for our experiment, and we use MD YBO4 laser as a fundamental wave, and we separate our optical system into two paths, and one path is for the fundamental wave, and the another one is for the reference wave. And for the reference wave, we normally use difference wave for the interference experiment to observe the 180-degree domain boundary, but this time, I'm not going to use interference experiment, so I'm only use a path one for our experiment today. So I will show you the first example about the ferroelastic calcium titanate. So this is a polarization microscope of images of calcium titanate, and there are two different kinds of domain boundaries in these materials. One is almost parallel to the lateral direction, and this is a major domain boundary. And also there is another type of domain boundary which is about 45-degree inclined from the another domain boundary. So we call this domain boundary as type A and type B domain boundary. And we selected this region and observed by using a second harmony generation microscope. And the result is shown on the right side. And the white region corresponds to the SHG active area and black to the non-SHG active area. And as you can see, when we compare with the polarization microscope image, we can clearly see that the domain boundary is SHG active for type A and type B domain boundaries. So we selected the area where the type A domain boundary and type B domain boundary coexist and performed a three-dimensional observation. And this is a result for the three-dimensional observation. So we simply measure the two-dimensional images with different depths. And this is a constructed images of 3D image of domain boundaries. So as you can see that the type A and type B domain boundary, even inside the domain, even inside the specimen, it remains SHG active. That means these domain boundaries can be polar even inside the specimen. And also we did a polarization analysis to determine the symmetry of domain boundary. And in the case of type B domain boundary, it can be fit with a monoclinic M. And this symmetry belongs to the polar group. So we can conclude that the domain boundary of calcium titanate is a polar. And also, we try to apply the stress because if we want to apply domain boundary for the application, it is necessary to control the domain boundary and also its properties. So we did some kind of tentative experiment by making this kind of apparatus. So we use a screw to apply the stress like this. And when we use this apparatus and measure it under the polarization microscope, and this is the result. So we are applying the stress parallel to the lateral direction. So when we increase the magnitude of the strain, the new domain boundaries start to appear from the edge of the specimen. And when we further increase the stress, these domain boundaries start to propagate into the middle of the specimen. And we selected this area and carried out a second harmony generation microscope observation. And this is a result for the SHG microscope observation. And as you can see, the newly appeared domain boundary by the stress is also the polar. And when we did the three-dimensional images, it's almost perpendicular to the sample surface. And also, the polarization analysis confirmed that the symmetry of newly appeared domain boundary is monoclinic M in the calcium titanate case. So now I will move to the second example about the lanthanum aluminate. So a lot of study, especially about the ferroelectricity at the domain boundary in ferroelastic material, is limited for the calcium titanate. And when I show the calcium titanate result, everybody asks me, why don't you do the other material? Why don't you try to the other material? So we are trying to do the lanthanum aluminate now. And there is a report in 2016, and they reported that they observed the polar nature at the domain boundary in lanthanum aluminate. So what they really observed, they created a tweed pattern domain boundary and performed the PFM measurement also, and also the RPS measurement. And they observed some kind of signal from the tweed pattern domain boundary in the case of lanthanum aluminate. So now I'm not going to talk about the tweed pattern domain boundary. I'm going to talk about the natural domain boundary I can observe in the lanthanum aluminate. So this is a polarization microscope image of lanthanum aluminate. And you can see there is only one type of domain boundary in this material. And when we select this area, we can observe and we observed it by using a second homogenization microscope. And as you can see that it also, the domain boundary of lanthanum aluminate is also also the SHG active. And when we did the three-dimensional images, we can see that even inside the specimen, it remains SHG active. So we did a polarization analysis for this measurement to determine the symmetry of this domain boundary. And when we change the direction of the polarizer and analyzer, and you can see that there is no SHG intensity except the domain boundary in these materials. And we select some area and perform the fitting by assuming the symmetry as the trigonal 3M, and it fits the experimental data quite well. And so we analyze this data according to the strength compatibility theory. And in the case of ferroelastic material, there are two types of domain boundary, and one is so-called double wall, and the other one is double prime wall. And in the case of lanthanum aluminate, because the phase transition is from M/3M to MMM, there are 9 domain boundaries, and all of them belong to the double wall, which is permitted by the crystallographical point of view. And the domain boundary that we observe this time is x equals 0 or y equals 0 domain boundary. So we confirm the polar nature of the domain boundary of lanthanum aluminate is polar in the case of double wall domain boundary. So now I will finish my presentation by summarizing my talks. So I show you 2 examples of the polar nature of the domain boundary in ferroelastic material. The first one is calcium titanate, and the second one is lanthanum aluminate. And both shows SHG active, and also this SHG activities remain even inside the specimen. And thank you very much for listening to my presentation.
Thank you. So we have time for a few questions. I'll start by asking one. So you showed that you were applying force to the material to contract it. Do you have any type of estimate to how much you were changing the lattice constant by, or how, like?
No, okay. Unfortunately, no.
Okay, okay. Any other? I guess everyone's quite ready for our coffee break. Oh, one question, or no? Okay, okay, yeah, okay.
What's the resolution of the SHG microscope?
Lateral reaction is about 500 nanometer, and the depth is 2 micron.
Well, maybe we'll thank all of our speakers again, and we have a half an hour break right now for coffee.